get fox hunt started up.
Really?
The signal strength meter is a big benefit for fox hunting.
All right.
No.
Kevin, can you see the slide?
Not yet. I just see the folder again.
All right. How about now?
Yep, I can see it now.
Okay. Except now I can't start it. Come on.
Oh. Oh, that's why I came in my truck.
Whoa. Where'd that come from?
That's still that system has gone up and it's bringing all that stuff around, some moisture or humidity.
How about now?
Better.
Okay. See, are we recording? Yeah. Okay, so now that we've got an antenna, we need to connect it up to our transmitter receiver. And we call those connections feed lines. It's usually coaxial cable. It could be what we call ladder line or twin lead or open wire. You're probably familiar with twin lead, which was what you used to use on an old TV to connect to an external antenna, little 300 ohm twin lead, which was about a 1/2 inch wide. Ladder line is similar, except it's about an inch wide, and it has holes punched in the plastic separator, so it makes it look more like a ladder, or in this case, a window. And then there's open wire, which is about 3 or 4 inches separation, but has little separators every so often, and it really looks like a ladder. It's actually one of the lowest loss feed lines. It's very, very low loss, but it's not easy to deal with. Coaxial cable is what you're going to find in most cases because it's easy, readily available. It's easy to route. You can get it with coatings that allow you to do direct burial, makes it waterproof, UV proof, or UV tolerant, I should say. After a while, UV is going to get to it eventually.
Especially here at Florida.
And it doesn't take any special tools, as opposed to hardline, which I have a piece lying there, which is in that case, it's a semi-rigid hardline, and it's got essentially air as the dielectric. So there's a little plastic spiral in there that separates the center conductor from that copper shell on the outside, or aluminum in that case shell. It takes special tools to put connectors on that because they need to be airtight. So you use that and larger versions of it for UHF stuff. Typically, you'll have hardline running to a repeater antenna because you're usually talking either VHF or UHF, and you might have a fairly long run up to the antenna, so you want to keep the losses at a minimum. Whereas normal coax at those frequencies has a lot more loss. Here's some pictures of a typical coax where you have a center conductor that could be solid or Makes it more flexible if it's stranded. It'll be surrounded with some form of dielectric. It could be a type of a foam plastic, or it could be a solid like polyethylene. And they have different dielectric properties, so it'll affect the velocity factor. That'll be surrounded by one or more outer shields. Typically, for the better coaxes, it will have an aluminum foil shield, and outside of that will be a copper braid, and then it'll have a jacket on it, which protects it from the weather. We mentioned window line or ladder line. That's the one in the center. The old twin lead is down here, and here's some pictures of hard line. In these examples, they're foam filled as opposed to air. The air ones have less loss than the ones with the foam.
And that's got a solid copper shield too, this.
Right. They're either copper or, in that case, aluminum, which makes it even harder to make connections to. You definitely can't solder it.
Yeah.
This is actual open wire. You see the spacers every so often. Don't see that much, but it's definitely a lot lower loss than coax. So one of the important parameters when you look at a feed line is its characteristic impedance. So if you take a piece of coax and you roll out a piece that's infinitely long, and you measure the impedance of it, that's going to be its characteristic impedance. So in the case of a typical coax, like a RG58 or RG8 or LM 400, it's going to be 50 ohms. So it turns out that if you take a shorter piece, not infinitely long, and you terminate it in its characteristic impedance, you only see the loss due to the actual resistance of the wire in the coax. And some dielectric loss, but it typically will allow you to get almost all of your power from one end to the other if it's terminated in its characteristic impedance. So in most cases, your transmitter is going to have a 50 ohm series output, and you want your antenna to be approximately 50 ohms. So you have a good match between the two, so you don't have reflected power coming back. So depending on the frequency you're running at and the loss of that particular coax, most of your power is going to get from one end to the other. You're going to have a little bit of ohmic loss and dielectric loss. Typically, in the HF range, most of these coaxes, you're going to be maybe a dB on 100 feet for the lower HF ranges. And we'll do a chart here showing examples of a couple of them. If you have done anything with cable TV, they use 75 ohm coax. That's the stuff you can go to Lowe's or Home Depot and buy, or you just buy it at Sears, 1/4 inch, 75 ohm cable. There's a long story on why amateur radio settled on 50 ohms as opposed to 75 ohms, or the other alternative was 35. Turns out 35 actually is better for power transmission. 75 was cheaper, which is why one of the reasons they use it for the TV industry. It's cheaper to manufacture per foot. So they compromised and see, how did they do it? They took the average of the mean of the 35 and the 75, and they came out with 49 point something. So that's where the 50 came from. When we talked about the characteristic impedance being 50 ohms, and the impedance, if you remember, is the opposition of AC current flow. We also measure it in ohms, just like we do DC resistance. And the formula for impedance, it's actually a vector quantity, but it has the real resistance, the ohmic resistance of the wire, plus the inductive and the capacitive reactances. And the capacitive reactance is normally a negative number. So when we say something's resonant, the inductive part, the J 2 pi FL, is going to be equal to the J over 2 pi FC. So they'll cancel out. So your impedance will be equal to R at resonance. Oops. I went too far. Oh, and the main thing is matching your transmitter output, your 50 ohms, to the antenna. So that you get maximum power transfer. So if your antenna is something other than 50, you're going to have to use some sort of matching network or just live with the difference. A typical half-wave dipole at a half wavelength height is like 72 ohms. So it's not a perfect match, but it's less than one, it's 1.5 SWR, which most people consider that workable. There's not that much loss. Now, if you're doing QRP, trying to run on 5 watts, you care about 1.5 SWR, a little bit more. And I think there used to be a thing that under an SWR of 2 was all right. Above 2 is, you need to work on it. Above 3,
That's bad.
most of the modern transceivers will start reducing power because it the high SWR can affect the output transistors. So in order to protect them, they'll reduce power automatically.
So then your resonance would be a lot higher,
It doesn't affect it much,
doesn't it?
no, but you've in the higher SWR, besides the loss, okay, is affecting the output transistors on the transmitter. That's really because that is a lot more expensive than a piece of coax. So why is coaxial cable the most common feed line for amateur radio antenna systems?
It's easy to use, requires few special tools,
Right.
especially if you get the ends with it.
Right. There you go. It just costs more to have somebody else put connectors on.
And they're easy to do, well, depending on what kind you get. What's going to be better? Soldered would be better than crimp, wouldn't it?
Actually, they claim crimp is preferable. You still, in most of them, you still solder the center conductor,
Right.
except for the LMR Easy Connects, where it actually goes into a little socket. You don't actually solder it, but those are $20 connectors, and they're type N connectors.
People like me are cheap.
Yeah, PL 259 is about $2.50, $3. What is impedance?
Opposition alpha.
Alpha.
Yep. What's the unit of impedance?
Delta.
All right. Okay, said most cases we're working with 50 ohms. Typically, you're going to be using something like RG58 or RG8X, which is 1/4 inch diameter coax inside your shack to connect things because it's a lot more flexible than the 1/2 inch coax. And you're talking about short pieces, so there isn't that much loss in it.
I got a 1 foot jumper cable and it's pretty thin, yeah.
Yeah. The RG213 is kind of a mil spec 1/2 inch cable, which they reference a lot. It's about the same as RG8 or LMR 400 as far as the specs. They're both 50 ohms, but there's probably 3 times more loss in the RG58 than there is in the 213. And here's the chart I talked about. And if we look at RG58, down here in the HF band, we go up to 28 megahertz. See, we're down only up to 2.4 dB loss at the 10-meter band. If we go over to 213, we're only 1 dB. And then as we go on up, you see a big difference where at VHF and UHF, we're 5.5 versus 2.4 and 9.9 versus 4.4. And then when you get up into the 2.4 gigahertz, which is your cell phone type range, 24.8 dB loss means you got no signal going to the antenna, basically.
Yeah, I've got that LMR 400 on mine as well.
Yeah,
So,
that's one of the best ones in the regular coax of 1/2 inch. Now there's an LMR 600, which is like 3/4 inch, which is lower.
that's a lot stiffer than the,
It's a lot stiffer and it's a lot more expensive.
yeah.
So what's the most common impedance of coaxial cables used in amateur radio? What happens as the frequency of a signal in coaxial cable is increased? I'll give you a hint. It has nothing to do with characteristic impedance.
Delta. Yeah, I go with you.
Right. The higher the frequency, the more the loss. What's the electrical difference between RG58 and 213 coaxial cable?
Charlie.
Yep. Okay. We're talking about here, you could get by with using something like RG58 for an 80-meter dipole because of the frequency. So your loss wouldn't be that bad. But if you tried to use, say, 50 feet of it at UHF, I mean, your loss is what, if you remember what was on the chart, it was what, 8, 9 dB, something like that for 100 feet. When you're doing VHF and UHF, particularly on things like repeaters, that's where the hardline type coax comes in. Because even the 213, you're starting to get some significant loss. I mean, it was up, what, 4 dB? Which is more than half loss. 3 dB is 50%. So which of the following types of feed line has the lowest loss at VHF and UHF?
Charlie.
Charlie. Okay, some of the things that can affect coax and increase the loss is if you get water intrusion, because it affects the dielectric. If you have a very high SWR and you have fairly high loss coax, you're going to get a lot of heating in it, which at some point could actually damage the dielectric, maybe even the outer sheet. Having an excess of connectors, because every connector is going to give you a little bit of loss and a mismatch. Normally they claim about 0.1 dB per connector, but it does add up. I mean, 5 of them would be half a dB, and you're starting to get noticeable. 1 dB is a 20% loss. A loose connector actually can cause other things like intermodulation distortion, but also loss because probably not making good connection on the shield, which is part of the circuit. And if it's loose enough that it's intermittent, it can act like a diode and create what we call intermodulation distortion. So any radio frequency waves that are in its path can do the intermodulation and create, re-radiate other frequencies. It's kind of a weird thing that can happen. Rusty bolts and things can do that too. Or it's not making a good connection. You don't think about that for normal stuff, but it does affect RF. Which of the following is a source of loss in coaxial feed line?
Delta.
All those things are bad. See, we talked about moisture. One of the ways moisture can get in is the ultraviolet can cause the outer sheath to kind of dry out and crack. So water can get in that way, which is why you want to, for any cable that's exposed, you want to make sure that you get UV tolerant cable. Not all the coax is going to be UV tolerant. And of course, hardline is very susceptible. You've got to make sure that however they do those connections, that they're all airtight, especially on the air insulated. Which of the following causes failure of coaxial cables? Why should the outer jacket of a coaxial cable be resistant to ultraviolet light?
Delta.
What's the disadvantage of air core coaxial cable when compared to foam or dielectric types?
Charlie, wouldn't it?
Charlie.
Okay, so remember, impedance is the opposition to AC current flow, where resistance is opposition to DC current. Well, to all current flow. Doesn't matter the frequency. We typically use coax for feed lines, 50 ohm, in probably 95% of the cases. The loss goes up with frequency. The 213 was less loss than the 58. The air insulated hard line is the lowest loss, particularly at VHF, UHF and above. And water intrusion in the connectors or the coax can create problems. And one of the ways it gets in is from UV.